Welcome everyone to another Gravity webinar. Today we are very glad to have with us Sergey Sibiryakov. Sergey got his PhD in Moscow in the Institute for Nuclear Research, and later he moved to CERN to do a postdoc there, also in Switzerland, in Lausanne, in the EPFL, École Polytechnique Fédérale de Lausanne. And later he got a longer position between CERN and Lausanne, and now he moved to Canada very recently, this weird year, and he's a member of McMaster University and Perimeter Institute, as you can see in the slides. And well, Sergey has worked in many topics all related to gravity, but he's most known for works in cosmology, in perturbation theory, and also in the study on some ideas for dark matter. And in particular for the topic he's going to talk about today, which is quantum gravity with a Lorentz violation or anisotropic scaling. So thank you very much, Sergey. And before letting you start, as he was asking, actually, if you have any question at any moment, please raise the hand. There is a button to raise the hand somewhere in the chat, or ask the question directly in the chat. I will be monitoring it, and I will ask it to Sergey, or I will tell you to start talking. Okay? So thank you, and Sergey, you can start.
Thank you, Mario. And thank you for invitations to talk here. Actually, it's very nice to see so many faces that I know, but unfortunately virtually. Yeah, would prefer to see all of you in person. Okay, we are living in a strange time. So yeah, as Mario said, feel free to ask questions. Well, not only by raising hands or in the chat, but also by interrupting me, because I really like being interactive. I think, yeah, with this online format, I think I like it even more, to be interrupted from time to time, not to get lost in the void of, I would say, of the World Wide Web. Yeah. Okay. So yeah, first let me acknowledge the contribution of my collaborators to what I will be talking about, yeah, without them, I think many of this work would not be done. And these collaborators are Diego Blas, whom I noticed is in the audience, Aurel Pujolas, Andrei Barvinsky, Mario, who is also in the audience, obviously, Christian Steinwachs, and yeah, recently Alexander Gurov. So yeah, let me start with some historical perspective. Okay, if I manage to go to the next slide. A second. Yeah. Okay, here it is. So yeah, so this idea was first proposed by Peter Horava in 2009, and then it became like incredibly popular. So you see, like, the citation rose, and it became actually so popular that he even managed, I think this paper even managed to get citations from 2001. And you see now it totals almost 2,000 citations. So this works well. Yeah, some of those works, I mean, were in the slot. Some of them were a bit too quick, I would say, because they tried to apply this idea, like, to solving various true or maybe assumed phenomenological puzzles, maybe without really understanding the foundation of this idea. And yeah, and that's probably, you know, explains this kind of delta functional almost peak in the beginning, but then, okay, things stabilized, and yeah, now I think it's kind of continuous line of research, yeah, with slowly decreasing citations, but that I think is common to most of papers, that, like, the citation curve goes down with time, but still getting, you know, like a lot of citations per year, like about 100. And what did we learn, you know, during these years? It's already almost 11 years. So we should have learned something. So what we learned, and actually that's what I kind of want you to take from this seminar, are the following. So first, the proposal, we learned that the proposal is mathematically consistent, because at first there was suspicion that maybe that's just totally wrong and doesn't make sense. So the answer is it does make sense, mathematically at least, as a consistent theory. So, moreover, some of the versions of this theory or this proposal, they do give rise to some UV complete models, as we wanted, actually, like full complete models of quantum gravity. So gravity in the sense that it describes dynamics of space-time. Yeah, at this point, I'm not yet saying how this gravity is related to general relativity that we like and that describes like universe at the energies where it was tested. But yeah, but these are some models of quantum gravity. And other models, other versions of this proposal, they are still under scrutiny, so they also may be consistent, may be complete or maybe not complete, and that's ongoing research. Then I think actually quite remarkable property of this proposal is that it is experimentally testable. So that's not like something we get too often, experimentally testable theory of quantum gravity. So I think that puts this proposal really apart, and actually I consider it as an advantage. Okay, maybe it's a bit too much of an advantage because probably it's already, well, it's already strongly constrained, at least again in some sense of parameter space, and might be eventually ruled out. But again, I think that would be quite remarkable. If it's ruled out by experiment, not by theoretical consistency, which is okay, but by experiment. And okay, that's basically already said. So more work is needed to understand what actually what happens. Is it still viable, like phenomenological experiment, like from observational viewpoint, or it will be eventually ruled out, or maybe it's already ruled out. We just haven't analyzed it in enough detail. Again, this is subject of ongoing work. That's what should be done probably next along these lines. Okay, so now the idea. So what the idea of this proposal? I think that just the main idea behind is that we want to quantize gravity, to make a theory of quantum gravity, but staying entirely within the realm of quantum field theory. So we don't want to introduce new concepts, new entities. Well, at least we want to restrict ourselves as much as possible. So we just want a quantum field theory, which is, by this I mean that it has usual properties. So it's unitary, it has finite number of fields. We can do calculation of this theory, so everything's under control. We don't need to speculate, and so on and so forth. Yeah, and okay, so that's the idea behind, and now let's go back and see where we start. So at the moment we have the general relativity, yeah, and that's really a beautiful theory, which is based on one hand, it can be considered as a geometric dynamics, a theory of geometry. On the other hand, it can be also understood from this quantum field theory viewpoint. It's a gauge theory. Well, it's a gauge theory. It's a classical gauge theory. It can be, of course, quantized. But once it is quantized, it predicts its own failure at very high energies or small distances. And okay, these are Planckian distances and Planckian energies, which are very high. We never reached them in experiments so far. But we know that the theory requires some UV completion above this Planck scale. And the question is, what is UV completion? And that's the issue of quantum gravity, or the question of quantum gravity. This is an old question, almost 100 years old. And of course, there are well-developed approaches to it. Probably the most developed one is string theory. Then there are other approaches causal dynamical triangulation, group quantum gravity, which are more questionable probably, or at least less developed. And there is this new, relatively new approach of quantum gravity with an asymptotic scaling. And all these approaches, they really have to somehow sacrifice one or another property of general relativity. So for example, string theory and like other approaches, most of them actually sacrifice the local field theory formalism. So they introduce new degrees of freedom, like string theory introduces strings, like elementary strings, which are not point-like objects. So it's not local in a strict sense anymore. Some form of locality is preserved, but really it's something different from the field theory. This approach of quantum gravity with anisotropic scaling, this sacrifices part of diff invariance. Okay, if you just look at it mathematically, okay, you say fine, just some, and we just reduce a bit gauge invariance. But of course, it has far-reaching consequences because reducing gauge invariance means that we are also reducing the global symmetries of, well, at least in this case, it will mean that we're also reducing global symmetries of the theory, and in particular, where we have to abundant Lorentz invariance at high energies. So okay, we'll discuss that later on. Good. Now, yeah, first let me try not to abandon Lorentz invariance, but no, sorry, yeah. In this slide, I just want to explain why GR predicts its own failure. So how can we understand that? Okay, so we start from the action of general relativity written here, and then we start treating it as a quantum field theory, doing perturbation theory around flat spacetime. Then, well, the first term will be the kinetic term for gravitons. Okay, I write it here schematically, but it's important that it contains two like metric field or two metric perturbations, H, and two derivatives. And of course, everything here is Lorentz invariant. So this derivative, they combine in something, some Lorentz scalar, like here box, or maybe there are some contractions with the metric indices. Okay, doesn't matter. And this is our leading quadratic part, and then the rest are perturbations. But now, what we want to do, we want to see how these perturbations, how they behave at short distances. Yeah, so we want to zoom in inside, zoom in, on short distances. For that, we do scaling transformation. That's a scale space-time coordinates. And according to the rules of the game, we should keep the quadratic part because if you want, that sets the amplitude of fluctuation, of quantum fluctuation. So we want to keep it invariant, and to do that, we have to rescale the metric perturbation in the following way. So so actually this like mathematical formula should be understood in the following sense, that on small scales, the fluctuations, quantum fluctuations of the metric, they scale like that with the distance on which we zoom. Where d here is the number of spatial coordinates, spatial dimensions. So if we are in 4 space-time dimensions, d is equal to 3. Okay, good. So that's how the fluctuation scale. And now we look how the interaction action scales. We substitute the scaling of the metric fluctuations here. We substitute the scaling of the coordinates, and that's what we get. So if d is bigger than 1, so if there is more than 1 spatial dimensions, this interaction actually grows at short distances. So d is bigger than 1. Yeah, when we zoom to small scales, like the interaction strength grows. Yeah, that's what is said here. And at some point, the interaction becomes bigger than the quadratic part, and we lose perturbative control. And actually, we lose control of the theory whatsoever. So we don't know what happens with the general relativity at shorter distances as quantum theory because of large quantum fluctuations. Are there questions concerning this point? Okay, let me then proceed. And here comes the one failed attempt, which is pretty old. So let's try to remedy somehow the scaling of interactions. So far without abandoning Lorentz invariance. Yes, so just within Lorentz invariant field theory. And though this is a failed attempt, I think it's quite instructive because it shows that you really cannot do that. So if we want to preserve kind of bound the interactions at short distances, we basically have to achieve that the scaling dimension of the metric perturbation is 0. Okay, why? Let me actually go here back. So because these interactions, if I just expand, this curvature tensor or the measure, they will contain more and more powers of the metric. It's an infinite series. And then whenever this metric perturbation has positive dimension, okay, at some point the interaction term will also have positive dimension, like positive scaling, positive scaling dimension. So we want to reduce the dimensionality of the metric perturbation to 0. And that can be achieved if we add to the Einstein term, we add higher curvature terms. Well, when I say higher curvature means like quadratic in the Ricci tensor and scalar. Okay, with some coefficients which I added. So in that case, these higher curvature terms at low energies, which we observe, they are irrelevant. So we don't see them. I mean, their effect is small because the curvature is much smaller than Planckian. But at short distances, at the distance of order Planckian, these terms start dominating. Why? Because they have more derivatives inside. So there's a question? Excuse me, I don't hear you. Can you talk louder?
Sergey, I'm afraid it's not a question.
It's not a question. Okay. Thanks, Paolo.
I was trying to see if I could understand it. I just muted it. You can continue.
Okay. So yeah, so at short distances. So yeah, these terms have more derivatives. So if I expand,
excuse me, can I ask a question?
Yeah, sure.
Hi. So why don't you use the Riemann tensor? Is there some special reason for that?
In 4 dimensions, the Riemann tensor up to total derivatives is equivalent to these two terms, to sum of these two terms.
Okay.
Yeah, in principle you can add the Riemann, but it's just equivalent. So yeah, so now they have more derivatives, and now if I expand the quadratic part, I get contribution from Einstein's term, but I also get contribution from these guys with 4 derivatives. Okay, and schematically this is some box to the 4th power, and just because there are more derivatives here at short distances, this term is bigger than that. Okay, so this term can be neglected, and this is the leading quadratic part in the action, and that sets a different scaling dimension of the metric perturbation. Actually, it turns out to be 0, and maybe in a more technical sense, it can be understood like, I mean, why it improves the behavior or the perturbative expansion for gravity. It can be understood in the following way: that the term gives you propagators, which are 1 over k to the 4th, not 1 over k squared, but 1 over k to the 4th, and that just improves convergence of perturbation theory integrals. Then, okay, people studied this theory, and it turns out to be well, actually, this naive argument turns out to be correct, though it requires some work to prove that the theory gets renormalizable now. So renormalizable means that we get rid of power law growth of interactions at short distances. Still, there could have been logarithmic growth of interactions. But it turns out that no, there is no logarithmic, even no logarithmic growth. In fact, instead the interactions become weaker at short distances. So in other words, the theory is asymptotically free. It's like QCD, where the coupling constant or the interaction become weaker and weaker when you go to shorter and shorter distances. And that's great. That sounds great because I mean, that looks like a complete quantum theory of gravity. But there's a problem. Actually, the problem comes precisely from the same higher derivative terms that cured, you know, like the other thing. But this because of this higher derivative terms, or if I take this 1 over k to the 4th propagator and actually expand it into simple poles, I will see that I will get a difference of 2 poles. Yes, so I get normal graviton pole, massless graviton pole, and some massive pole, but with negative sign. And of course, I need negative sign. I cannot do anything, you know, to change this negative sign, this minus sign to plus, without screwing up this 1 over k to the 4th behavior. Or in other words, if I want to get 1 over k to the 4th behavior, I need to have minus sign here. But minus sign is very bad because it means, yeah, if I just kind of translate this expression into spectral density, it means that my spectral density is negative. So, which contradicts unitary. So it cannot be true in unitary series. So in this way, basically, we prove that, you know, these terms, they violate unitary. So the theory cannot be unitary. And no, that's a big problem because we don't know how to deal with non-unitary series. We don't know even what it is. Okay, so this fails. And now, what was the new twist that Horava suggested? He said, "Okay, yeah, let's do something, maybe, yeah, out of despair." Let's imagine that our space-time is endowed with another geometric structure, namely foliation into space-like surfaces, hypersurfaces. So, well, physically, it would mean that I have some notion of preferred time. And this foliation sets like the coordinate that runs perpendicular to the surfaces. This is a time coordinate, and along the surfaces, I have spatial coordinates. That necessarily reduces the symmetry of the series. So now we have to preserve this foliation structure. So our full group of diffeomorphisms is reduced to foliation preserving diffeomorphism. Okay, some subgroup. But that's fine. Okay, so let's try to stick to this idea and see where it leads us. And and then let's write Lagrangians which have more than two derivatives, but not in all directions, but only in space, and keep two derivatives in time. So if we manage to do that, then we will avoid having costs. Yeah, we will, well, at least we have a chance to preserve unitarity. But on the other hand, additional derivatives in space, we can hope that they will improve convergence of loop integrals, and eventually we'll get a series which is renormalizable. And there is a nice way to formalize this statement that we want to improve convergence of loop integrals using the notion of anisotropic scaling symmetry, which actually is well known in condensed matter physics, where time and space naturally enter at different footings. And yeah, so let us, but so the idea here is that let us introduce like additional derivatives in space, and then when we do the scaling exercise, when we study how our fields and interaction scale with when we zoom on shorter distances, we will scale space and time in a different way to preserve, like the structure of the quadratic action. So here is again schematically schematic expression. So our quadratic action, it's an integral over space and time naturally. Then we have a kinetic part. Let's call it kinetic part, which contains time derivatives, and here we allow only two time derivatives. And we have another part. Let's call it potential part. Okay, with some abuse of language. Where like Laplacian now enters into some power. So it's not like this z is different from 1 generically. So yeah, in the relativistic series, this z, this critical exponent, okay, it's called sometime, is necessarily 1, but here we allow it to be different. And then we do rescaling so that we rescale time and space differently, and again see what's the scaling rules. What are the scaling rules for the metric? And here they are. Yeah, the scaling rule for the metric that preserve this quadratic action. And you see here we can, if we allow ourselves to play with z, we can make dimensionality of h 0. Yeah. So if we want, for example, theory in 3 space dimensions plus 1 time, so d is equal to 3, we just choose z equals 3. And yeah, the scaling dimension of the metric is 0 now. Okay, so that's I think like the simplified idea. Now we have to implement it in some yeah. Now we still have to write some kind of Lagrangian that has this property.
I have a question.
Yes, please.
So before in the previous slides, or in general, when you were writing Hij, before I was thinking that you are using diffeomorphisms to gauge fix H0, 0 and H0i to 0. but now you have less gauge freedom. Why are you still writing Hij?
Yes, good point. Because, well, this is just for simplification. In fact, these other components, they come now on this slide. So previous slide was just simplification, kind of forgetting, you know, about H00 and H0i, what we want to do with Hij. But of course, to have the full, in the full theory, we'll get other components as well. And yeah, now I'm gonna discuss yeah, it's kind of, it's from what I said, it's not yet clear that we will be able to write an action which contains all these other components as well and has this property. Here I agree with you. And yeah, and I think that's kind of crux of the it's non-trivial part of the whole task. I mean, to introduce this other these other fields properly, and also to prove afterwards that like gauge fixing procedure does not screw up this naive this naive scaling argument. Okay. So yeah, yeah, I think it should be clear after a few slides, but if not, ask me again. Okay, so yeah, so here we are. So now the first thing that we want to preserve as many symmetries as possible. In principle, once we allow ourselves to reduce the full group of diffeos, we probably can play with different options. I mean, having less and less symmetries, and then we have more and more freedom in writing down the action of this theory. But I think the first, probably, yeah, if you want to call it conservative approach, is to keep as many symmetries as possible. So we keep all transformations or coordinate transformations that preserve the foliation structure. And what they are. So they are as follows. So I can make any transformation of space coordinates, which depend both on space and time. And I can do arbitrary scaling of time, arbitrary reparameterization of time, but here it depends only on time. Because yeah, if I allowed here X dependence, that would mean I'm changing these foliations, which I'm not allowed to do. And then associated to this transformation, to the gauge transformations, there are gauge fields. So first, there is a gamma ij spatial metric, which just reflects the fact that we can do arbitrary like diffeomorphisms in three-dimensional slices. But because the diffeomorphisms depend on time, we also have a gauge field for that, which is Ni, and which can be identified with the H0i components of the metric in the covariant formalism. And associated to this time reparameterization, we have another gauge field, N. Well, I will call it lapse function from time to time, which is an analog of H00. So yes, in principle, we have all these fields here. And yeah, and then I can, once I have that, I can write down the Lagrangian. Yeah, I still have to specify the scaling dimensions, I think, of this Ni and N. And this I will do by writing down the Lagrangian and then just reading out if I can make proper scaling assignments to Ni and N, so that the whole Lagrangian obeys like scaling symmetry that I want to implement. So what is here in this Lagrangian? So in this Lagrangian, I have kinetic part for the metric, which is formulated in terms of extrinsic curvature of foliation slices, Kij. So Kij expression is here. Well, I think yeah, the expression is not that important. What is important is that it contains time derivatives, and only one time derivative. So this action is first order in time derivatives of gamma Ij. And it does not contain time derivatives of shift of this Ni, and it does not contain time derivatives of N. This is due to the symmetries. The symmetries forbid that. And then, yeah, the proper dimensionality assignment for these additional fields is that the lapse function has 0 dimension, the same as the spatial metric, and the shift function, this Ni, has dimensionality d-1. So it's space-time dimension -1, because yeah, I want this object Kij to scale homogeneously. Okay, so this is the kinetic part. In fact, I can write another term in the kinetic part where I take the trace of K, and it comes now with an arbitrary coefficient in front, arbitrary dimensionless parameter of the theory. And here I have a potential part, which I don't write explicitly because it's more complicated, but which can contain, where I should actually include all terms with up to 2 times the number of spatial, with the number of spatial derivatives up to twice the number of spatial dimensions. So if we are in 3 spatial dimensions, I have to include here terms with up to 6 spatial derivatives. All terms which are invariant under this symmetry. And yeah, one can work out that there is only a finite number of them, though in principle this number is quite large in general. Yeah, when I say in general, in fact, there are 2 versions of this construction, and they differ by what I assume about the Slabs function n. So the first version got the name non-projectable, is when I assume that this n is an arbitrary field, which depends on time and space. The field. And then the number of terms in the potential is really large, because I also can include derivatives, spatial derivatives of n, but finite. And another version is which is called projectable. And in that case, basically one notices that this symmetry can be implemented just having a function of time. So you don't need n to depend on x. So we will just say that n is a function of time. Yeah, in this sense, you kind of project out x dependence. And yeah, at first it may look that this is a bit weird. This may look weird, this condition. It's like we are introducing some non-locality in space. You may think it's like global, yes, global variable over the whole space. Okay. Yes.
Sorry,
yes, Mario. Yes.
So maybe you should turn off your camera.
Okay. Thanks for saying that. Yeah. Let me see. Where is my camera? How can I? Yeah. Just a second. I probably stop video. Okay, now, do you hear me now?
Yes.
Mario, yeah,
yes,
perfect. Okay, so yeah, I was saying that this may look like non-locality, but in fact, probably the simplest way to understand this projectable version is just to say that we'll gauge out this n field by using this symmetry. So we'll remove this n, this Slabs function altogether from the theory and together with this symmetry. So we'll be just left with spatial diffeomorphisms depending arbitrarily on time and corresponding gauge fields. Yes. Yeah, yeah, maybe at this point it may seem that this theory has nothing to do with general relativity whatsoever. It cannot be any way close to general relativity, but in fact, it turns out that it can. And okay, that probably will come by the end of the talk, but yeah, but just to assure you that it's not completely detached from what we know about gravity. Okay. Yeah. Right. Okay. So now the question is, okay, I think the theoretical question. Yeah, so here I'm not going in historical order. So first, when the theory appeared, people precisely addressed whether it has anything to do with GR or not. But for me, let me kind of pretend that I don't care about GR at this point and just see if just understand if this theory does fulfill the expectations, if it really provides a UV complete theory. And 2 things we have to check are the following. So first, we have to check whether the theory is renormalizable. Yeah, we want normal quantum field theory. And if it's not renormalizable, then we will get, again, the power law growth of interactions at short distances or at large energies. And then we are not doing better than general relativity. So, okay, so that's the first question. And second question is more subtle. because even if we have renormalizability, we still may have Landau poles, which correspond to logarithmic growth of interactions. So now these poles can be exponentially at exponentially large distance, large energies, but this is still bad, yeah, because the theory is not complete. So we'll still need some additional decompletion. So that's the second question we want to address.
Can I ask another question?
Yes.
Third question.
Yes.
Is it? Yeah. What about locality? You mentioned, but I didn't get the answer. Does it have microcausality? I guess there's no light cone.
There is no light cone. No. There is some important notion of locality that we want to preserve, and that kind of is wrapped in this renormalizability question. Yes.
Okay, so then I wait.
Yeah. So actually, it's rather here on this slide. So actually, why? So first, we probably let's make one step back and ask ourselves actually why this power counting argument, why we actually believe it works at all. I mean, this scaling argument, why we expect that it somehow improves the theory. And the naive proof, it goes like as follows: naive proof of renormalizability. So what we are working with? We are working in quantum field theory. We are working with path integrals. So we have some partition function, which is path integral over variables with action. Okay. So then in perturbation theory, we expand this path integral in series of interaction Lagrangian, and we are getting, like integrals of this kind. Which are divergent, of course. As we know, these integrals are divergent, and these are UV divergences, which we want to renormalize, somehow remove. And now we say, if our interaction action has negative or non-positive dimensionality, then the whole structure here has non-positive dimensionality with respect to whatever scaling symmetry we introduced. Fine. Okay, so this has non-positive dimensionality. Then, if divergences are local, and that's what happens in normal relativistic quantum field theory, that's guaranteed. So these divergences, like these products, are well defined whenever these products are well defined whenever the points are different, are apart from each other, and the only divergence they come when some of these arguments collide together. So the divergences are local. So they produce local operators. And then, because the whole dimensionality of this thing is non-positive, the dimensionality of divergence is also non-positive. Good. So we will have to remove this divergence by introducing some operator in the action with non-positive dimension. But we already included all these operators in the bare action if we follow our rules of the game. So it means that we'll need to renormalize the couplings in front of these operators. So okay, so that's naive argument, and it relies on two statements, which kind of implicitly, or I try to make them explicit, that the divergences are local, and that actually all operators that are generated by these divergences are already present in the action. And this argument, as it's stated here, has an important caveat, because both these properties can be violated by fixing the gauge. And in gauge series, we have to fix the gauge. We have to introduce gauge fixing term. So we break the gauge, we break gauge invariance explicitly. And this may introduce in this kind of series non-locality, because it can spoil the power counting properties of the propagators. And actually, the operators I generate here, they are not gauge invariant. They are, because of my breaking of gauge invariance, I generate all operators. Well, I generate operators which are not gauge invariant, and I have to check that I can still package them in a gauge invariant form. Okay, that's a bit of simplification. The formal reasoning goes through BRST invariance, introducing like Gauss sector, and then ensure that the whole action has BRST symmetry, and this BRST symmetry is preserved by renormalization. So yeah, so just to reiterate again, so this naive power counting argument in gauge series does not work automatically because gauge fixing can spoil power counting, locality, and unitarity, essentially everything. So to proceed, we need like the best way to proceed is to find a family of nice gauges where power counting or scaling is manifestly preserved. And this is a non-trivial task, even in well-known examples like standard models. So like introduction of arc psi gauge in standard models, that that was a big achievement. Well, essentially a Nobel Prize with Veltman and Toft go for that. Yeah. So so here the task is the same. Actually, it's more complicated. Well, it's probably even a bit, well, somewhat more complicated because of absence of Lorentz invariance. So and that introduces additional kind of degree of freedom in choosing the gauges, and like generic gauge would break power counting properties. And the second thing one has to do is to prove that gauge invariance, or as I said, BRST symmetry more technically, is preserved at all orders of perturbation theory, which also is not automatic. And yeah, again, maybe this can be traced back to absence of Lorentz invariant, because we are more used to Lorentz invariant series, where Lorentz invariance imposes additional restrictions of type of operators we can get. And here you can get, like, the freedom is bigger, and proving that BRST invariance, BRST symmetry is preserved is a bit more complicated. But I won't go into details. The punchline is that this has been done. I mean, both these points were achieved for projectable Horava-Lifshitz gravity. So, yeah, in projectile case, we have this proof. In non-projectile case, we still don't have a proof. Basically, no gauges which would manifestly have this, like, preserve this property of power counting and locality have not been found. And that seems to be, well, that does not mean that these non-projectable series are not renormalizable, but most likely, analyzing them will require, like, more explicit tracking of potential non-local divergences. And here, like, we have an intermediate summary of this research. Okay, so projectile case is renormalizable. Yeah, in general, actually in any number of dimensions. Non-projectable, we don't know.
Can I ask a question?
Yes.
So why don't you do a, so usually if I allow myself to do a non-relativistic gauge fixing, I can completely fix it and forget about, or not to introduce any ghost fits. Why isn't it the case here? In fact, here, since you don't have Lorentz, then it seems to be even more appropriate.
Yes, that introduces non-locality in space.
But aren't you already non-local?
No.
You mean the Lagrangian terms are local? Okay.
Yes, Lagrangian is local, and if I introduce, if I use gauge fixing, like Coulomb gauge. Yeah, I think okay. What is important is the following. So these nice gauges that were found, they have the following property. So all propagators of all fields in these gauges, they depend on frequency and momentum, on both of them, and they kind of decrease uniformly when you scale frequency and momentum with Lifshitz scaling. They decrease uniformly in all directions. Now, if I introduce a general gauge, in particular, like analog of Coulomb gauge or something like this, so that I don't introduce ghosts, then I will get terms which scale only with momentum or only with frequency, but do not scale homogeneously in all directions. Do not fall down, homogeneously in all directions, and that spoils this manifest locality, which I'm talking about. So I want to keep well, instead of Lorentz invariant propagator, which kind of automatically it's 1 over p squared, so then it scales in all directions the same way. Now here I don't have that, but I want a propagator which behaves like 1 over omega squared plus k to the 6 or whatever. But it's important that there is this plus there, omega squared plus k to the 6. If I just have 1 over omega squared, that's bad. That introduces non-locality. Does it answer your question?
Yes. Thanks.
Okay. Okay, so now we address the second item. We address whether we can get U-complete theory. And here we need to sit down and actually perform calculation of the renormalization group, which is hard. It's a hard task. So first, let us start from something simplest. And something simplest is the version of this model in 2+1 dimension, where let's consider projectable version because this is the one which is renormalizable. So in 2+1 dimension, the full Lagrangian just has this form. So it is this kinetic part, kij and k square, and in the potential part, I can have only r square, spatial curvature squared. So this RSP, and that means spatial curvature, two-dimensional curvature. And then there are just 3 coupling constants, g, lambda, u, in this Lagrangian. So we have to study the normalization of these constants. There are g running. This theory is non-trivial, unlike GR, because general relativity in 3 dimensions does not have any propagating degrees of freedom. So it may have some non-trivial global dynamics, but there is no local dynamics without sources. I'm now discussing. So this theory does have non-trivial local dynamics because it has an additional degree of freedom compared to gravity. And in this case, it's just a scalar. Well, actually, it's always a scalar, but in 2+1 dimension, we have just 1 scalar degree of freedom. So in principle, this can be thought of, or this is a like a variant of scalar field theory in 2+1 dimensions, but very weird one. So it's a gauge theory of scalars in 2+1. And there are some consistency conditions where these couplings should be not to violate unitarity, not to have instabilities or costs, something like this. The slide. This slide is a bit technical, just saying that actually separately, this G and mu are not. Considering separately the running of G and mu is meaningless because the beta functions of this G and mu are actually gauge dependent, as it happens with non-essential coupling. So that is known in usual gauge series, that there are essential couplings whose renormalization does not depend on gauge fixing choice, and there are non-essential couplings which, in general, whose beta functions are gauge dependent. So, but they don't then characterize any physics. So again, just to make the story short, the physics in this model is actually characterized just by two couplings: lambda, which is already there, and a ratio of G over square root of mu. And this second coupling, this curly G, should be understood as a coupling, like is something reflecting the strength of the interaction. So if this curly G is large, interaction is strong. If it's small, it's weak. So we are going to compute the beta function of these two guys, lambda and curly G. And yes.
Really? Are the black hole solutions in 3D?
Yeah, you are going very fast. I think we have been struggling with this question of black holes. Yeah, okay. Let me make a small digression. We have been struggling for how much time? Year or so?
Close to 2 years, Sergey. Close to 2 years.
More than a year, yeah. So we don't know yet. Okay, the true answer is that we don't know. But that's okay. Of course, that's kind of question which appears very natural because we want to understand the, we want to, I mean, if we have here this nice theory, I mean, why not studying black holes in it and see what they do? But but it turns out not to be easy to find even classical solutions. We can come, we can discuss it after the talk.
Is the statement about 3D or more generally?
Yeah, it's a statement that we don't know if in this projectable series, if there are black holes, we still don't know. About projectable series, we don't know. In non-projectable series, we know that there are black holes. In non-projectable series, they're somewhat closer to GR, to general relativity. And then there are large black holes, at least, which are similar to general relativistic black holes. Projectable series, they are further away from general relativity, and for them, we don't know if there are black holes or not.
Okay, thanks.
Just let me use the chance, Sergey. There was a few questions, so you have like 10 minutes left. A bit left. Okay.
10 minutes. Okay, good. So yeah, so here I will go quick. Yeah, probably I skipped these technical details. We just sit down and calculate. And these are, okay, the answer is here. These are the beta functions that we found. And an important, like really crucial finding is this minus sign in this expression. So yeah, you can notice that this expression, the whole expression is actually positive, but there is a minus sign in front. Yeah. So well, it's probably not obvious, but one can check that actually this quadratic form is positive definite. So then there is minus sign, which means that the beta function of this curly G is negative, which signals asymptotic freedom. And to make it more pictorial, so here we have the RG flow in the theory, and the errors, as usual, they show the flow towards infrared. So if we start from here, that means that this is the fixed point in UV. So this is an ultraviolet fixed point. And you see that it corresponds to zero G, so to zero interaction. That's where the theory wants to be in the ultraviolet. And it's also good that it corresponds to some lambda, which is of order 1, because lambda is actually not a coupling constant. It's a parameter in the Lagrangian, and essentially, it enters in some way in the dispersion relation of the scalar, which is the only dynamical degree of freedom, local degree of freedom in this theory. And this dispersion relation is kind of, it's consistent, is well behaved, as long as lambda stays away from this region between 1/2 and 1. So if it takes this value, this quite weird value, 15/14, with just numerical result. So if it stays here, then everything is all right. So this is the asymptotically free fixed point of this theory. And also, it's interesting what happens when in the infrared. So we see that the theory flows from this fixed point. Okay, it can flow to large values of lambda, but it can also flow in this direction towards lambda equal 1. And lambda equal 1 naively is the limit of general relativity. So at least, again, just naively, the theory can go somewhat closer to general relativity in the infrared. Well, the true story is more complicated because when lambda approaches 1, the theory becomes strongly coupled. So one can look at the loop corrections and one sees that these corrections become large.
Sorry,
yes.
Lambda was the coefficient of trace k squared, right?
Yes.
So then should I know something about the spatial derivative to say it's becoming Lorentz invariant? Because I think you said that lambda equals 1 corresponds to.
Okay, maybe I first should explain why. Yeah, well, let's say why it's cut, because just looking already at beta functions, we see lambda in the name. So like this distribution, yeah, which is a beta function, we see that the diversion number becomes close to 1. That's one of the simple manifestations of this regime.
Sergey, we cannot hear you right now. There are a lot of interferences.
I can jump in to answer while he.
Okay, well, he reconnects.
But the reason is that the special part, there are two special parts. One, which is the Ricci scalar, which in 2+1 is topological, so it doesn't really matter. And the other one is R square, which in principle, yeah, it's true that it's a high order term. So no, that makes sense what I'm saying. Do you hear me?
Yes, I'm here. I'm thinking.
Yeah. Well, it's true that you cannot. The thing is that you cannot recover. You cannot recover exactly a Lorentz invariant theory in this kind of wiggly couple flows, because you are going from a theory with 1 degree of freedom, which is this theory with an extra R squared, to a theory which is GR in 2+1, where there are no degrees of freedom. So in this sense, it is naive. What Sergey is saying, that the flow takes you to a strong. Yeah.
Does it mean that in the IR I float to an empty theory?
You float to a kind of a strongly coupled theory that it is not, well, you don't really know what's going on there, right? It's going to be some dynamics. So you go exactly to the point that corresponds to the Lorentz invariant case. Yeah, it would be like an empty, but you can never float to this empty theory, no? Because you have degrees of freedom somewhere, somehow. So this is an interesting point.
Work with this PDF. Okay, you see now the PDF file, yeah?
Yes, you can keep on. You have like a few minutes, 5, 6.
Yeah. No. Minutes. Yeah. Just let's. So it's okay. So you see. Okay, good. So yeah, I skipped the story about 3+1 dimensions. But basically in 3+1 dimension, the study is ongoing. And there are some signs that it can share this property of asymptotic freedom as 2+1 dimension. So now here we have this chart. So basically in 2+1 dimensions, we have a theory which is renormalizable and asymptotically free, and it's a theory of quantum gravity. In 3+1 dimension, we have a theory which is renormalizable. It's asymptotically free. Okay, we still need to finish the calculation. And yeah, non-projectable, we don't know. Okay, so that was good. So this is we answer theoretical questions. So this framework does provide some theories of quantum gravity, but then do they have anything to do with general relativity? And for that we need to go to low energy limit now. So energy is much smaller than Planckian, and there what we find that actually all these theories, they reduce to a scalar tensor gravity. So in this sense, they are just consistent. So they describe one transverse traces, graviton, and scalars. Where the scalar comes from, it's easy to understand from this picture of foliations. So basically, the scalar describes the foliation structure, and each foliation surface corresponds to a constant value of the scalar. So these are like layers. Then, like the most relevant parameter is the overall coefficient in front of the action of the scalar. It has dimension of mass similar to Planck mass, and let's call it Horava scale, which in principle can be different from Planck mass. We probably a priori expect it to be close to Planckian, but it may be below. You still hear me? Yes.
Yes, we hear you.
Okay, thanks. And then yeah, the scalar tensor theory, this action for the scalar is not Lorentz invariant. Yeah, this first part, usual general relativity action, is Lorentz invariant, but the second part is not. Yeah, because the scalar describes this Lorentz violating structure. So because of that, the dispersion relations for excitations do not really propagate with the speed of light. So there is here, for example, for gravitons, there is a correction, which I call epsilon, which is of order of the ratio, this mh squared to m Planck squared. And there are higher derivative terms with higher powers of moment, suppressed by this scale mh. Yes. So that's as far as transverse traceless degree of freedom go. Okay, they have nice dispersion relations. I mean, healthy dispersion relations, but with different velocity from the speed of light. For scalars, it's a bit more complicated. For non-projectable case, the scalar has also well-defined dispersion relation with some positive coefficient in front of k square and higher derivative terms. So this non-projectable case is stable. I mean, the scalar is stable, and if this Horava scale is low enough compared to Planck scale, then it produces GR. In fact, phenomenology of GR. Again, just because in that case, this whole contribution, the scalar contribution, is suppressed, and we work just with general relativity to leading order. Project case, which we found to be very well behaved in the ultraviolet, in the infrared is actually ill behaved, because the scalar gets a negative coefficient in front of its dispersion relation. So it describes an instability. At short distances, this instability is fixed by higher derivative terms, because I mean, they have positive coefficients in front. So there is something like plus k to the 4. But this is only, I mean, this is only at high energies. At low energies, we have this instability. In other words, there is no Minkowski vacuum in this theory. Yeah, I think in the zeroth approximation, this is phenomenological disaster for a projectable case. So this is probably we have to say that at least in the zeroth approximation, the projectable case is a distant cousin of general relativity. Whereas non-projectable is there is a smooth limit. Yeah, there is some limit in which this non-projectable recovers general relativity. But even for non-projectable, there is a challenge, because as I said, it predicts generically like velocities of gravity waves different from one or from the speed of light, from electromagnetic waves. And actually for all particles, in general, the velocities can be different. But then we know from experiment that, like from different collider or astroparticle observations, we know that all velocities of all particles are actually the same and equal to the speed of light. So for example, for protons, like the difference between proton and the photon velocity is at the level 10 to minus 22, like extremely small, and well, should be less than 10 to minus 22. And for gravitons, the difference should be less than 10 to minus 15, as we learned from a recent observation of binary neutron star coalescence together with electromagnetic signal. So this looks like a severe constraint on the theory, and yeah, at the very least requires severe fine-tuning. So does it mean that the whole program is dead? Maybe, yeah. I must say that probably it's yeah, at least it's under very strong stress. But I think it's already remarkable that we kind of managed to make a quantum gravity theory which is ruled out by experiments. So it's testable, yeah, and even testable to the extent that it's almost ruled out. There is one probably small hope that I think it's worth exploring, or at least the possibility that is worth exploring. That possibility is Lorentz invariance can emerge dynamically as a low energy property. And though it sounds maybe like speculative, in fact, there are many examples of series, and both in particle physics, but well, particle physics, I mean, when we discuss extensions of particle physics series, Or in condensed matter, that's actually quite generic phenomenon, emergence of Lorentz invariance at low energies, as a result of renormalization group flow towards infrared. And there is actually a reason, a good reason why that should happen. Because because there is a theorem that Lorentz invariant fixed points are attractive in the infrared. So okay, when I say but that solves the problem. Not yet, because we really need now, the question is now quantitative. We need, to flow towards this Lorentz invariant fixed point very close to it. Yeah, we need to be very close to it, or we need to approach it very fast as we go from energies like Planck energies down to energy that we observe at colliders. And even that can be achieved in principle if the series is strongly coupled. So in non-gravitational series, one can analyze what levels of suppression one can achieve, and in principle, one can achieve power law suppression in the parameter, like in the hierarchy of energy scales, which may be enough to satisfy experimental constraints. Then there is another observation that if the series is asymptotically free, and actually in 3 dimensions it is asymptotically free, then it flows naturally to strong coupling in the infrared. So it looks like this ingredient is present in this construction almost for free. But of course, there is a disclaimer here that this mechanism of emergence of Lorentz invariance has not been worked out at all for gravity. Probably just because we never had a series of strong coupling in quantum gravity, which would be under control. And now is the first time when we have that. We have a series which is asymptotically free, so it's well under control, and the questions about strong coupling in the infrared is well posed. And very speculative idea that maybe somehow the strong coupling can also resolve the issue of vacuum instability in the projectable case. I don't know. Well, we can discuss that, but that's I must agree that this is a quite speculative idea. Okay, so here's summary. You are still with me, right?
Yes.
Perfect. So summary. Projectile Horava-Lifshitz models, they represent a class of normalizable gravity series. And they're series in the sense that they have a large subgroup of different variants that prevents from having local gauge invariant observables. So this property shares general relativity. And it features spin 2 degrees of freedom in dimensions higher than. In 3 dimensions, this is asymptotically free, and as such, it is UV complete. And that probably can be the case also in 3. In IR, and then I think there is already an interesting question per se. What does it mean? Gravitational theory in strong coupling. What is that? I mean, how we should describe that? What are the relevant observables or relevant questions to ask? Do we get a kind of gravitational confinement in this at low energies with decoupling of some degrees of freedom, or maybe all degrees of freedom? We get an empty theory, or we get a non-trivial fixed point in the infrared. So these are now well-posed questions, and they can be studied well, at least numerically. We still don't have an answer about renormalizability of non-projectable version, not to say anything about its asymptotic freedom or not. But here we really know little. And from the phenomenological perspective, these gravitational wave measurements, they present the most serious probably challenge to this framework, to the whole work. And if the challenge is not addressed, then this probably will remain pure theoretical exercise, which still can learn us, can teach us something. We still can learn something from. Actually, we already learned something. So here are the open questions, and one really major question, central question, I think, is whether this emergence of Lorentz invariance through strong coupling, whether the strong coupling in the infrared can somehow lead to emergent Lorentz invariance at low energies. Yeah, then I would say if this happens, then I would say the theory is almost automatically general relativity, because we have a theorem. If we have a Lorentz invariant theory of gravity, then it should be of spin two fields, then it should be general relativity. So yeah, so in this scenario, like the dynamical renormalization group flow would lead to general relativity infrared. If this does not happen, somehow this emergence of Lorentz invariance does not happen, or it doesn't happen with enough precision, I think we can still use this Horava gravity as a toy model to address puzzles of general relativity. So one is characterization of observables, for example. Yeah, there are no local gauge invariant observables. So what shall we look for? What are the well-defined observables? Yeah, we can also think about resolution of singularities, which would be present there in general relativity if this framework somehow allows to resolve them. And yeah, one would like also to address information paradox, but here I have question mark, because we first, yeah, probably I should have added here like another item. We first need to understand if there are black hole solutions in the series or not, and if there are, and yeah, in which sense they are black holes. Yeah, if they exist, do they have horizons or not? Yeah, are there solutions with horizons or not? And if there are, then how the information paradox is resolved. But these are all open questions, so there are plenty of open questions to address here. Thank you for your attention, and yeah, I'm ready to take more questions. And thank you for questions that have been already asked.
Thank you very much, Sergey. And it seems that we've finally been able to finish.
Yeah.
Okay, now it's time for questions. There is first a question on the chat, which I'm going to read from Andreas, and then I will ask to some other people. Okay, so let me read it. Thank you, Sergey, for your nice talk. I have a question. There have been works applying the functional renormalization group methodology to projectable Horava gravity, Saueressig, Benedetti, etc. Could you perhaps contrast the results obtained studying its perturbative renormalizability to this?
I think they agree. I mean, yeah, as far as I can tell, the results of just diagrammatic expansion agree with the results of functional renormalization group whenever the series is weakly coupled. So yeah, well, some of those studies, as far as I remember, they could have made some truncation, so they could consider only low energy limit of the theory or some other restrictions. But in principle, like in general, I believe what they found is consistent with what we find. So in those, whenever our results, our frameworks overlap. Now, maybe this functional renormalization group may allow to go further to strongly coupled regime. But that is a complicated. Yeah, I think
we are losing you again.
And that's the way to go.
Okay, we lost you like for 10 seconds.
Yeah, I was saying. Yeah, I said that. Well, essentially. Do you hear me now? Or?
Badly. There are someone is trying to censor us.
What? I will stop sharing. No, I will stop sharing.
Yeah, stop sharing the screen.
So, yeah, yeah.
Okay, I think we lost him again. Yeah.
Our setups overlap. The studies of functional renormalization group agree with the perturbative studies. To go beyond perturbative studies, one needs something more. Yeah, either some clever version of this functional renormalization group, or causal dynamical triangulation, or I don't know, or maybe some Hamiltonian transcation. Yeah, but yeah, some numerical method.
Okay, and then he's asking again Well, thanks for your reply. So in the strongly coupling regime, there could perhaps be an interacting fixed point?
Yes, that would be super interesting.
Okay, so any other question? So, okay.
Mario?
Yeah.
I can ask a quick one if there is time.
Hi, Marco.
Okay. Thanks for your talk. And I have a naive question. So can you say in few words what's wrong with the non-projectable Horava? So why is so difficult to find, let's say, to show the renormalizability or respect to the projectable one?
Yes. In that case, yeah, it's hard to preserve manifest locality. So what you get? Yeah. Okay. I will give you technical answer first. So technically, you get that some of the propagators of the fields, they do not fall uniformly in frequency and momentum. So they fall down only in, say, momentum. And then the frequency integrals, loop integrals in frequency, they diverge. They have additional divergence because there is no suppression in frequency. And these divergences are not local in space. Yeah, and the choice of the gauge doesn't help here. This is physical, actually. This is physical statement. So there are some degrees of freedom which like propagate instantaneously, if you want. Even at, well, at 3 level already, though the action is local. These degrees of freedom, they are associated to a symmetry, to this to this time reparameterization symmetry. So there is like a hope that maybe this divergence cancel if I just start really computing loops. This divergence cancel because of this symmetry, because of some word identities associated to this symmetry.
But the symmetry between the projectable and non-projectable, you have the same f-diffs.
Yes, but time reparameterizations in projectable, we get rid of them whatsoever, and together with their associated laps. In non-projectable, this symmetry, we cannot get rid of it. We cannot eliminate it completely, and we have lapse function which is dynamical, and this lapse function precisely has this non-local property. It's a bit like Coulomb field, yeah, in electromagnetism. So I think, well, at least the way I'm talking about these word identities, but we haven't found them yet. So maybe there are no word identities. But then we should sit down and calculate, which is hard. And see if this non-local divergence cancel or not. If they don't cancel, then we are screwed, and this theory does not really, how to say, is not renormalizable. That's it, the end of the story. But maybe some, yeah. But if they cancel, then we'll have to understand what is behind that cancellation. So that's what makes non-projectable different from projectable. Though it sounds like a technical issue, but actually it changes a lot the physics.
Okay, thanks.
Okay, so I think this is the point to stop. Thank you again, Sergey, for the talk. It was very nice, even though the connection problems.
Yeah, sorry for the connection problems.